We gaze at the night sky and don't even realize how deeply we're mistaken. It's in our blood, from the first fire flickering in the darkness of caves to the giant antennas pointing into the abyss of space. We have never stopped believing in one thing, that all of this makes sense because we exist, that we are the center, that we are the reason, that we are the answer. But there is one image that destroys all of that, a pale blue dot. A photograph taken by Voyager 1 from a distance of 6 billion kilometers. One last look back. One last chance to see ourselves as we truly are. And do you know what you see there? Nothing. No grandeur, no history, no humanity. Just a microscopic flash of light lost in the dead, indifferent darkness that couldn't care less whether we exist or not. In this pixel, all the wars, all the empires, all the geniuses and all the forgotten names, all your fears, all your dreams, all the love you've ever felt, compressed into nothing. And the scariest part isn't even that. The scariest thing is that looking at this pixel, we stubbornly refuse to accept it. We still whisper, "This is special." We still call it home. We still convince ourselves that amidst this boundless darkness, we matter. But the cosmos is silent. And in that silence lies the answer we're afraid to hear. And if this thought has touched you, stay with me, subscribe and like, so we can walk this path to the end together. We have convinced ourselves that the small blue world is the absolute masterpiece of nature, that the conditions here on this particular orbit, around this particular yellow star, are the perfect standard, the benchmark, the meter preserved in the chamber of weights and measures of cosmic biology. When our astronomers peer through the lenses of telescopes, searching for exoplanets around other stars, they are looking for Earth 2.0. They are searching for a mirror. They are searching for a copy of our home because they sincerely believe what we have here is the best the universe can offer. But what if we are catastrophically, fundamentally wrong? What if our boundless love for Earth is nothing more than a Stockholm syndrome on a planetary scale? We love it because we survived here. We adapted to its whims, to its cruelty, and now we perceive these scars of evolution as proof of its perfection. But let us take off these rose-colored glasses of anthropocentrism. Let us look at our home not as enamored poets, but as dispassionate cosmic engineers evaluating a project. If we face the truth, Earth is not a luxurious palace created for the carefree flourishing of life. Earth is more like an old, unstable house on the outskirts of a galactic neighborhood, a house where the roof constantly leaks, where the foundation cracks at the seams, and the heating system functions so erratically that the inhabitants are constantly balancing between freezing and heat stroke. We call Earth Mother. But this mother has tried to kill us countless times. Earth's history is not a peaceful idyll of continuous progress. It is a brutal, bloody chronicle of geological and climatic chaos. Life on our planet is not an honored guest given the finest chambers. It is more like a stubborn weed pushing through asphalt, constantly risking being crushed. Recall the mass extinctions. There were five times this perfect world became so hostile that the biosphere stood on the brink of total erasure. Approximately 252 million years ago, an event occurred that paleontologists whisperingly call the Great Dying, the Permian-Triassic extinction. Our perfect planet fractured. massive flows of magma, known as the Siberian Traps, broke through the Earth's crust, pouring out millions of cubic kilometers of molten rock. The atmosphere filled with toxic gases. The oceans became so acidic that the shells of marine organisms dissolved directly in the water. Temperatures skyrocketed. Earth turned into a true hell. 96% of all marine species and 70% of terrestrial vertebrates vanished. Does this resemble the behavior of an ideal environment? Does a perfect home fill its rooms with hydrogen sulfide and set its floors on fire? And what about cold? Our planet has an extremely unstable thermostat. Several times in its history, Earth experienced periods known as snowball Earth. Imagine this. Glaciers a kilometer thick advanced from the poles and met at the very equator. The entire ocean was locked beneath armor of ice. Life, which had only just begun experimenting with multicellularity, was driven into dark, narrow refuges near underwater volcanoes, trembling while waiting for the planet to decide to warm again. Our atmosphere, which we are so proud of, is an incredibly thin and vulnerable film. It is held by gravity that is strong enough to keep us from drifting into space, but not strong enough to hold a dense, truly protective layer forever. Our magnetic field, a shield against deadly solar radiation, is generated by a molten iron core that is slowly but inevitably cooling. One day, this shield will fall, just as it fell on Mars, and the solar wind will begin stripping away our sky layer by layer. Earth is a compromise. It is a planet that simply ended up in the right place at the right time and had enough luck for life to take hold of its changing surface. It lies within the so-called Goldilocks zone, the habitable zone where water can exist in liquid form. But being in this zone is only a minimum requirement. It is like having a pulse. It means the patient is alive, but it does not mean they possess Olympic health. For decades, astrobiologists searched for mirrors. They used Earth as the only possible template. If a planet was slightly larger, it was discarded. If a star was slightly dimmer, the system was ignored. We were blinded by our own reflection. But science evolves. The mind expands its boundaries. In the early 2010s, within a narrow circle of theoreticians, astrophysicists, and climatologists, a heretical idea began to emerge. They looked at computer models of planetary systems, played with masses, orbits, atmospheric compositions, and types of stars, and suddenly saw a mathematical truth that shattered the Earth standard. They asked themselves, if Earth barely meets the criteria of a safe long-term home, if its history is a sequence of catastrophes that life barely survived, then might the laws of physics and chemistry allow the existence of something better? Could there exist a world where the biosphere does not need to rebuild itself from ashes every 100 million years? A world where conditions are not merely acceptable, but optimal? A world designed for life as perfectly as waters designed for fish? Thus, a new revolutionary term appeared in the scientific lexicon: superhabitable worlds. The word super here does not simply mean bigger or cooler in a vulgar sense. In the language of astrophysics, it indicates a higher degree of suitability. It is a concept of planets or moons whose fundamental physical characteristics, mass, temperature, age, position within the system, and the nature of the parent star, create an environment that supports a broader spectrum of biodiversity and does so for a significantly longer time than Earth. This is a paradigm shift, comparable to the discovery of Copernicus. Copernicus moved Earth from the center of the solar system. The concept of superhabitable worlds removes Earth from the pedestal of biological perfection. It tells us, Earth is not the summit of the mountain. Earth is merely a base camp on its slope, and the true summit, the true paradise garden, is hidden somewhere among billions of stars, pulsing with life in forms and scales we can barely imagine. Scientists began searching for these worlds not out of curiosity, but from a deep understanding. If we want to find truly ancient, powerful, and all-encompassing life in the universe, we must stop searching for our own reflections. We must look for places where life never had to struggle for survival with such desperate brutality. We must seek greenhouse worlds, cradle worlds that never froze and never dried out. And when we begin constructing these worlds in our mathematical models, when we assemble the perfect mass, the perfect atmosphere, and the perfect star, before us emerges a picture that makes Earth's landscape seem dim and pale. But to understand what this paradise looks like, we must first understand the main flaw of our own world, a flaw that hangs above us every day, giving us life, yet at the same time relentlessly counting down the time to our inevitable end. We must look at the sun. When we lift our eyes to the sky, we see the source of all our existence. Throughout the entire history of humanity, from the very origins of our consciousness, we have worshipped this blinding circle of light. Our ancestors built gigantic stone observatories for it, composed hymns in its honor, offered it sacrifices, and called it by the names of the most powerful deities: Ra, Helios, Apollo, Inti, Dazbog. For us, the sun is the absolute symbol of eternity, stability, and the unchanging order of things. It rises every morning, driving away the darkness, and sets every evening, allowing us to rest. It seems to us an unshakable foundation upon which the entire complex mechanism of earthly life is built. We perceive its light as something given, as a constant that has always existed and will exist for an infinitely long time. But this view is deeply illusory. It is the perspective of beings whose lives last only a few moments on the cosmic clock. If we cast aside our human measure of time and look at the sun through the eyes of the universe, we will see a completely different picture. We will see not an eternal God, but merely a temporary flare, a fleeting spark that with every second inexorably approaches its extinction. Our parent star, a yellow dwarf of spectral class G, is not at all an ideal machine for sustaining life. In fact, from the point of view of long-term biological evolution, our sun has one fundamental fatal flaw that makes Earth only a temporary rented dwelling from which we will inevitably be evicted. This flaw is time. There is catastrophically little of it. The sun, like any other star of this type, has its strictly defined life cycle. It is not a bottomless well of energy. It is a gigantic thermonuclear reactor that every second burns millions of tons of hydrogen fuel, converting it into helium in its extremely dense and scorching core. This process releases an enormous amount of energy, which counteracts the incredible force of gravity trying to compress the star. As long as this balance holds, the star lives and shines, but the fuel is not infinite. The total lifespan of our star on the so-called main sequence, that is, during the period of stable hydrogen burning, is approximately 10 billion years. For the human mind, this number seems immeasurable, astronomical, almost synonymous with eternity. But let us examine it through the lens of biological evolution. Our planet, Earth, is now about 4.5 billion years old. It formed from a gas and dust cloud shortly after the birth of the sun itself. The first forms of life, simple primitive single-celled organisms, archaea and bacteria, appeared in the primordial oceans quite quickly, perhaps within a few 100 million years after the Earth's crust cooled enough to hold liquid water. But what happened next? What followed was a time of incredibly slow, painful waiting. For nearly 3 billion years, life on Earth remained blind, mute, and microscopic. For 3 billion years, the oceans were filled only with bacterial mats and cyanobacteria. 3 billion years. That is 1/3 of the entire life cycle of our star. Evolution did not hurry. It encountered obstacles. It waited for random mutations, for changes in the chemical composition of the atmosphere, for tectonic shifts. Only when our planet crossed the threshold of 4 billion years did the so-called Cambrian explosion occur, a sudden and explosive emergence of complex multicellular life forms, animals with hard shells, eyes, and complex behavior. That is, Earth required 4 billion years, or nearly half of the entire lifetime of the Sun, just to create something more complex than microscopic slime. We, humans, with our consciousness, language, culture, and technologies, appeared literally in the final second of the cosmic day. We are the product of an evolution that lasted almost half of the time allotted to our star. The Sun is now at the midpoint of its life. It is a middle-aged star, and we are accustomed to thinking that we still have a full 5 billion years of stability ahead before the Sun exhausts its hydrogen, expands into a red giant, and engulfs Mercury, Venus, and possibly even Earth itself in its blazing plasma belly. But this is yet another great illusion. The end for our world will come much, much sooner. The fact is that stars of spectral class G are not static during their lifetimes. As hydrogen in the core is converted into helium, the core becomes denser and hotter. To maintain balance against gravity, the outer layers of the star are forced to radiate more energy. The Sun gradually, imperceptibly to the human eye, but inevitably, becomes brighter and hotter. Since its birth, it has already become approximately 30% brighter, and this process is accelerating. We do not need to wait 5 billion years for the Sun to become a red giant to witness the death of our biosphere. The harsh mathematics of astrophysics tells us that our planet has very little time left. In just 1 billion years, the Sun's luminosity will increase by another approximately 10%. For us, here on Earth, these 10% will be a sentence. They will cross a critical threshold beyond which there will be no return. The gradual increase in temperature will trigger a chain reaction. First, the evaporation of water from the oceans will intensify. Water vapor is a powerful greenhouse gas, far stronger than carbon dioxide. The more vapor enters the atmosphere, the more heat will be trapped near the planet's surface, which in turn will lead to even more evaporation. This is the so-called runaway greenhouse effect. Surface temperatures will begin to rise rapidly. Geological processes will also change. Rising temperatures will accelerate the weathering of silicate rocks, leading to a sharp drop in atmospheric carbon dioxide levels. Plants that depend on photosynthesis will begin to die off en masse from starvation. When carbon dioxide levels fall below a critical threshold, forests, grasses, and algae will disappear. Herbivores will inevitably follow, and then predators. Food chains will collapse into ash. Within 1 billion years, our beautiful, deep blue oceans will literally begin to boil. Water will evaporate into the stratosphere, where solar radiation will mercilessly split water molecules into oxygen and hydrogen. The light hydrogen will escape forever into space. Earth will begin irreversibly losing its water. The planet we call the Blue Pearl will turn into a scorched, dry, dead desert, similar to present-day Venus, where surface temperatures reach hundreds of degrees Celsius and the sky is covered with thick, toxic clouds. 1 billion years. That is how much time remains for multicellular life on Earth. If we look at the bigger picture, the window of opportunity for a complex biosphere on our planet is only about 1.5 billion years out of the total 10 billion years of our system's existence. This is merely a brief moment of clarity between endless epochs of dead silence. Life on Earth is not an eternal celebration. It is rather a desperate temporary flash, a spark struck by chance, which will inevitably fade long before our star enters its final stages. Yellow dwarfs like our Sun simply do not give evolution enough time for true, unhurried, limitless development. They are too active, too changeable, too short-lived. Earth is a world that is constantly under threat of eviction. But if we expand our search, if we abandon the bias that only sun-like stars can give rise to life, we will find the true winners of the cosmic lottery. We will find stars that embody stability, calm, and endless time. These are stars that astronomers call orange dwarfs, or stars of spectral class K. They are not the most common stars in the universe. That title belongs to red dwarfs, small, dim, and extremely long-lived stars. Red dwarfs can shine for trillions of years. Their lives are so long that since the moment of the Big Bang, not a single red dwarf has yet had time to die of old age. But they have their terrible drawbacks. In their youth, they are often extremely active, unleashing gigantic flares of deadly X-ray and ultraviolet radiation capable of stripping the atmosphere from any planet that dares to come too close. And to receive enough heat from such a dim star, a planet must orbit very closely, which often leads to tidal locking, when the planet always faces the star with only one side. On one hemisphere, there is eternal scorching day. On the other, eternal freezing night. It is an environment of extremes, far from ideal. But orange dwarfs of class K are the perfect golden mean. They are a true cosmic compromise that combines the best traits of both worlds, while leaving their drawbacks behind. These stars are slightly smaller than our Sun. They have masses ranging from 50 to 80% of the Sun's mass. Their surface temperature is lower, their radiation less intense, but still powerful enough to warm planets on safe, comfortable orbits, where there is no threat of tidal locking or deadly stellar storms. But their most important advantage lies in the speed of their internal thermonuclear reactor. Because they are less massive, the gravitational pressure in their interiors is weaker. Accordingly, nuclear fusion reactions proceed much more slowly, calmly, and efficiently. Orange dwarfs do not burn their fuel at the frantic, uncontrollable rate of our Sun. They behave like careful stewards, distributing their resources evenly over an incredibly long period. If the life cycle of our Sun is measured at 10 billion years, then the stable phase of an orange dwarf lasts from 20 to 70 billion years. Think about that scale. 70 billion years. That is 5 times longer than the current age of the entire universe, which is now about 13.5 billion years old. This is not just a lot of time. It is deep, fundamental, geological, and biological calm. It is eternity embodied in matter. Imagine a planet orbiting such a star. A world where life does not need to hurry. A world where evolution has 5, even 7 times more time for its experiments than it had on Earth. On our planet, evolution often operates in panic mode. It is driven by global climate changes, asteroid impacts, continental drift, and the inevitable increase in solar activity. Species must constantly adapt, change, or go extinct. It is a race for survival where there are no winners, only those who manage to delay their defeat. But under the gentle, unchanging light of an orange dwarf, the rules of the game change radically. When the environment remains stable not for millions but for tens of billions of years, evolution ceases to be merely a mechanism for survival under crisis conditions. It becomes a tool of absolute refinement. Life does not simply fill ecological niches. It weaves itself into networks so complex, deeply integrated, and interdependent that the entire biosphere begins to function as a single, perfectly tuned superorganism. When you have 50 billion years of continuous calm development, the need for brutal competition disappears. Instead, symbiosis begins to dominate. Organisms learn to coexist at the molecular level. exchanging resources with maximum efficiency. Animals and plants, fungi and bacteria form alliances that on Earth would seem fantastical. Life integrates with the planet itself, beginning to control its geological cycles, the chemistry of its oceans, the composition of its atmosphere, maintaining a perfect balance on its own. This is biology that has reached its highest philosophical maturity. It is not just life. It is the art of existence brought to an absolute through the boundless luxury of time. But what would nature look like in such a world? How would it be perceived by our senses if we somehow found ourselves on the surface of this superhabitable planet, beneath a sky illuminated by an orange dwarf? We are accustomed to our yellow-white sun, which at clear noon blinds the eyes and casts sharp, deep black shadows. Our light carries aggression. It delivers a massive dose of harsh ultraviolet radiation. This radiation is invisible, yet it acts like a microscopic scalpel, constantly attacking, tearing, and damaging the strands of DNA molecules in every cell of our skin. In every leaf of a plant, life on Earth is forced to expend enormous amounts of energy simply to constantly repair this microscopic damage, to create protective pigments, to hide from direct rays. Our sun both gives life and slowly burns it away. But a Class K star behaves very differently. It has a lower surface temperature, around 4,000 degrees Celsius, compared to nearly 6,000 degrees for our sun. Because of this, the peak of its radiation is shifted from the blue-green and ultraviolet part of the spectrum into the red, orange, and infrared regions. Imagine this landscape. The sky above this planet would never have that bright, piercing, sometimes painfully intense blue color we are used to in summer. The light of the orange dwarf would scatter differently in the atmosphere, creating a dome of extraordinarily soft, deep hues. Perhaps it would be the color of ripe peach, or molten gold, or soft, rich copper. The star in the sky would appear somewhat larger than our sun, because the habitable zone around a dimmer star lies closer to it, a vast, calm, orange-red disk hanging above the horizon, not blinding the eyes but enveloping everything in a warm, dense glow. This light lacks aggressive harshness. There is no dangerous ultraviolet radiation forcing biology into constant defense. This radiation is gentle. It warms, penetrates deep into tissues, stimulates chemical processes without destroying molecular structures. On Earth, we call the time just before sunset the golden hour. These are the brief moments when shadows grow long, the light becomes incredibly soft and warm, and all colors become rich and deep. It is the time when the world seems most peaceful and beautiful, when the wind calms and the outlines of objects lose their sharpness. On Earth, this magic lasts only a few dozen minutes before darkness falls. But on a planet around a Class K star, this golden hour lasts forever. It is not a fleeting state. It is a constant, fundamental property of the environment, an eternal, gentle, relaxing midday. The absence of sharp shadows creates a sense of visual softness across the entire landscape, where light seems to flow around objects rather than cutting space in half. And the nature of this world, evolving under this light for tens of billions of years, would appear completely alien to us, yet infinitely beautiful. We are used to green being the dominant color of life on Earth. Our plants use chlorophyll, a pigment that absorbs red and blue wavelengths of sunlight while reflecting green, which are most intense in the spectrum of our yellow dwarf. But under an orange sun, this mechanism would be highly inefficient. To capture as much life-giving energy as possible from a star that emits primarily red and infrared light, local flora would have to adapt. Plants here would not be green. Their leaves and photosynthetic surfaces would contain different pigments, much darker ones, capable of absorbing a broader range of available light. Instead of familiar green forests, we would see vast expanses of vegetation in deep burgundy, rich purple, dark indigo, or even absolute black like onyx. Imagine an endless ancient forest where the leaves have the color of thick red wine, faintly shimmering under the soft rays of an eternal orange sun. These black-red jungles would absorb every drop of light falling from the sky, converting it into boundless biological energy without wasting anything. Water in rivers and shallow seas would reflect the copper sky, creating landscapes resembling molten amber. This would be a world of deep, monumental calm, a world where the star is not a tyrant that punishes with heat or radiation, not a ticking bomb counting down the final millions of years until the oceans evaporate. A Class K star is a careful guardian. It gives life the most valuable and rare resource in the entire universe. It gives it time. Time measured in tens of billions of years. Time sufficient for evolution to surpass itself, creating a symphony of life so complex and perfect that, by comparison, the entire history of Earth would seem like only a rough first sketch of a beginner. The sun gave us the chance to appear, but stars like orange dwarfs are the true temples of eternal life. And when we realize this difference, our attachment to our home star begins to fill with a subtle, almost imperceptible sadness. We're children of a temporary world, looking into eternity, knowing that it belongs to others, that a perfect star requires a perfect planet, and as we continue our impartial cosmic audit, Earth fails the casting again and again. The geometry of true paradise dictates entirely different rules, and the most fundamental concerns mass. A planet that aspires to the status of an absolute cradle of life must be significantly larger than our fragile blue home. We are accustomed to measuring the world by ourselves and our planet. For us, Earth's gravity is an unshakable constant. Its radius is the yardstick of all distances, and its mass is the unit from which we derive all our calculations. But the universe did not create Earth as a standard. Our mass is merely a coincidence in the chaotic process of merging cosmic dust and rock. Billions of years ago, researchers, armed with the most powerful supercomputers and the laws of physics, have modeled thousands of scenarios of planetary evolution and reached a striking conclusion. The ideal superworld is a planet whose mass is approximately 1.5 times that of Earth. Why exactly 1.5 times? Why does size play such an absolute critical role in the long-term flourishing of a biosphere? Why not twice? Why not 3 times larger? The answer lies not on the surface, but in the deepest, darkest layers of planetary anatomy. It lies where pressure is immense and temperatures approach those on the surface of stars. It lies in the heart of the planet. A larger planet means a significantly more massive metallic core. To understand why this is so important, we must look at a planet not as a chunk of rock, but as a giant, extraordinarily complex thermodynamic engine. At the center of our Earth lies a sphere of molten iron and nickel. This sphere is constantly moving, churning, and mixing due to immense internal heat. These powerful convective flows of liquid metal, rotating together with the planet itself, act like a colossal dynamo. It is this continuous motion of incandescent iron deep beneath our feet that generates Earth's magnetic field. This magnetic field is not just an invisible abstraction that makes a compass needle point north. It is our only, absolutely indispensable shield. Our planet is constantly under bombardment. Space is not empty. It is filled with the solar wind, a relentless stream of high-energy charged particles traveling from the sun at hundreds of kilometers per second. Without our magnetic field, this noscaput radiation would strike directly at our atmosphere. It would tear air molecules apart and simply blow them into open space, drop by drop, ton by ton, until nothing remained of our luxurious blue sky but a black, lifeless vacuum. But any engine eventually cools. The law of conservation of energy and the laws of thermodynamics are unforgiving. From the moment of its formation, every planet slowly but inevitably loses its internal heat to the cold, indifferent void of space. And here, the ruthless geometry known as the square-cube law comes into play. Smaller objects cool much faster than larger ones because their surface area through which heat is lost is large relative to their internal volume, which stores that heat. Look at Mars. It is the perfect and the saddest illustration of this law. Billions of years ago, Mars was not a dead, rust-colored desert. It had rivers, deep lakes, a thick atmosphere, and perhaps even primitive life. But Mars has only 1/10 the mass of Earth. It was too small. Its internal volume could not retain its primordial heat for long. Its iron core cooled and solidified. The great planetary dynamo stopped. Convective currents froze, and at the very moment Mars's heart stopped, its magnetic field vanished. Without this invisible shield, the solar wind crashed unimpeded into the Martian skies. Over millions of years, it systematically stripped away the planet's atmosphere, layer by layer, carrying off oxygen, nitrogen, and water vapor. The remaining water either froze or evaporated and was likewise dispersed into interstellar space. Mars did not die from a sudden catastrophe. It died because it was geometrically inadequate. It died from the cold in its own core. Earth is larger, and so its heart still beats. Our magnetic shield still holds. But even our planet is gradually cooling. One day in the unimaginably distant future, Earth's core will also crystallize and stop. Our atmosphere will become vulnerable as well. We are only temporary travelers in cosmic time. Now imagine a super-Earth 1.5 times more massive. A more massive iron core is a colossal reservoir of internal thermal energy. Thanks to the same square-cube law, such a planet would cool incredibly slowly. Its internal dynamo would operate not for billions but for tens of billions of years. The molten metal flows in its depths would be more powerful, generating a magnetic field far stronger and more stable than Earth's. It would be an eternal, absolutely unbreakable shield. No solar storms, no cosmic cataclysms, no radiation bursts could penetrate this defense. The magnetosphere of such a world would extend far into space, deflecting any threat, instead of auroras visible only at high latitudes. On this planet, gigantic shimmering ribbons of light orange, purple, green might sometimes stretch across the entire sky all the way to the equator during intense stellar storms, reminding its inhabitants of the overwhelming strength of their planetary shield. On such a super-Earth, life would never know the terror of cosmic radiation. It would exist within a fortress whose walls are built from the very fundamentals of physics, but mass affects more than invisible magnetic fields. It has a direct, physical, almost tangible influence on what we breathe. Stronger gravity means stronger arms with which the planet holds everything on its surface, including gases. Earth's atmosphere is, in fact, an extraordinarily thin, fragile film. If we imagine Earth as the size of an apple, then all of our atmosphere, our clouds, winds, and air currents would be no thicker than the apple's skin. Our gravity holds this air, but gas molecules are constantly moving, and the lightest of them occasionally reach escape velocity at the upper layers of the atmosphere and drift off into space. Earth slowly but constantly leaks. A planet 1.5 times more massive would have gravity roughly a quarter stronger. This is not the kind of gravity that would crush bones and turn movement into agony. No, it would simply be slightly greater weight, to which biological species could easily adapt by developing stronger muscles and sturdier support structures. But for the atmosphere, this increasing gravity would be decisive. Stronger gravity would hold the atmospheric blanket more tightly, preventing gases from dissipating. It would compress this blanket closer to the surface. The atmosphere of such a superworld would be significantly thicker, denser, and richer. Atmospheric pressure at sea level could be 2 or even 3 times higher than on Earth. For us, being there would feel like descending a few meters underwater. We would sense pressure in our ears, but our bodies could still function. For local life, however, this density would open entirely new and extraordinary possibilities. Imagine air with such remarkable physical density. It would no longer be an invisible emptiness as it is on Earth. It would become an almost tangible medium, a kind of extremely light, transparent ocean enveloping the entire planet. In such dense gas, the laws of aerodynamics work differently. Flight, which on Earth is a constant and exhausting struggle against gravity requiring immense energy and extremely light, fragile bones, would cease to be a challenge. In such a world, winged creatures would not need to frantically flap their wings to stay aloft. The medium itself would support them. They could glide effortlessly for hours, for days, like oceanic rays drifting through water. Thanks to the high density of the air, lift would be so great that colossal creatures with wingspans that would seem structurally impossible on Earth could take to the skies. Even the heaviest animals might possess membranes or skin folds, enabling long leaps and gliding flights between the crowns of massive, towering trees. And how would this world sound? In a denser medium, sound waves propagate differently. Sounds would be deeper, richer, and travel much farther. The songs of native creatures might carry for hundreds of kilometers, rolling across endless valleys like the low, vibrating hum of an organ. Dense air would hold more moisture, more scents, creating an incredibly S4's squatternefran Guinefoto symphony for those who rely on smell. It would be an atmosphere in which life is literally dissolved in every cubic centimeter of space and atmosphere that does not merely support breathing, but serves as a full arena for the most complex evolutionary dances. But the geometric consequences do not end there. High gravity has another profound and fundamental effect on a planet's appearance. It smooths the landscape. Matter has limits to its strength. On Earth, the highest point is Mount Everest, rising nearly 9 kilometers above sea level. Why are there no mountains 15 or 20 kilometers high? Because rock is not infinitely strong. When a mountain becomes too massive, its own weight, under Earth's gravity, exerts such pressure at its base that the rock begins to deform, crumble, and flow like plastic. Earth does not allow mountains to grow beyond a certain limit. Now apply this logic to a super-Earth with gravity a quarter stronger than ours. Geological conditions become far harsher. Stronger gravity would prevent tectonic forces from pushing rock to such extreme heights. Mountains there would never reach the grandeur or sharpness of Earth's Himalayas or Andes. They would be lower, smoother, more like vast, rolling hills. More importantly, this same gravity would prevent the formation of extremely deep ocean trenches. Earth has the Mariana Trench, a chasm 11 kilometers deep, an absolute darkness where pressure is so immense that iron spheres would be crushed flat. Our oceans, in general, are extraordinarily deep. And while this may sound romantic, a boundless blue abyss from a biological perspective, it is actually a major limitation. The deep ocean deserts of Earth are largely lifeless. Sunlight penetrates only a few dozen meters, at most 200. Beyond that lies eternal darkness. Photosynthesis is impossible. There are no plants. Food chains are sparse, sustained only by the slow fall of organic debris from the illuminated upper layers. Most of the volume of our oceans is a vast, cold, dark desert that contributes little to overall biodiversity. On a super-Earth, however, where gravity smooths the terrain like a colossal press, the geometry of water would be entirely different. Ocean basins would be shallower. Tectonic plates pressed more evenly against the hot mantle would form flatter continental platforms. Instead of collecting in deep, narrow basins, water would spread across the surface in a wide but shallow layer. This world would not be divided into massive continents and deep, isolated oceans. Water would simply flood the lowlands, forming endless systems of shallow seas, bays, lagoons, and straits. The entire planet would become a vast global archipelago. Not one or two continents, but millions, tens of millions of islands of all sizes. From tiny sandbars to land masses the size of Australia, scattered across the globe. These islands would be connected by the most intricate natural architecture imaginable, endless coral reefs and underwater forests. And here lies the greatest triumph of such planetary geometry. We know from Earth that life flourishes most intensely in shallow waters, where sunlight reaches the nutrient-rich seabed. Coral reefs cover less than 0.1% of the ocean's surface, yet they host more than 25% of all known marine species. Now imagine a planet where nearly the entire ocean is one continuous global reef. A planet where a gentle, eternal orange sun warms and illuminates the seabed across most of its waters. The absence of deep, cold dead zones would mean that nearly every square meter of this aquatic world is a massive reactor of biomass production. Every island, surrounded by shallow seas, would be an evolutionary laboratory, yet still connected to others through currents and passages, allowing species to mix, compete, cooperate, and give rise to ever more complex forms of life. This would be a biosphere not confined to narrow coastal strips as on Earth, but one that spreads freely, abundantly, and endlessly across the entire planet. The geometry of a super-Earth, its greater mass, stronger gravity, and smoother terrain would not merely create conditions for life. It would create a perfect vessel, filled to the brim with life that never knows scarcity of space, light, or warmth. Now let's push even further in our construction of absolute perfection. We have already chosen the ideal star for our world, a calm, long-lived orange dwarf. We have shaped a planet with the perfect mass, 1.5 times that of Earth, equipping it with a permanent magnetic shield and a dense, reliable atmosphere. We have smoothed its terrain, turning the surface into an endless archipelago of shallow seas, where water flows freely from horizon to horizon. But for this flawlessly engineered mechanism to truly come alive and operate at full, unstoppable power, we must approach the main control panel of the planetary climate. We must set the baseline thermostat. An ideal planet designed for the triumph of biology must not be as cold, harsh, and thermally unstable as our home Earth. We humans are asquafixness to our climate and consider it normal, but from an objective thermodynamic perspective, Earth today exists in a state of chronic underheating. The average surface temperature of our planet is only about 15 degrees Celsius. For us, this feels comfortable. But for the global biosphere, it is a delicate balance on the edge between life and dormancy. 15 degrees is the temperature of a world constantly glancing over its shoulder, waiting for winter. A truly superhabitable world must be different. Its ideal baseline temperature should be, on average, 5 degrees warmer than Earth. At first glance, a difference of 5 degrees may seem insignificant. In daily life, the difference between 15 and 20 degrees is just a matter of whether to wear a light jacket in the evening. But when we are talking about the global average temperature of an entire planet, those 5 degrees become a colossal, fundamental shift in the very architecture of reality. A global increase of 5 degrees completely and permanently rewrites the rules for every living cell, every microorganism, every drop of water in the ocean. To understand the scale of this change, we must first acknowledge the harshest truth about Earth. A vast portion of our planet is completely unsuitable for active life because of cold. Forget our pride in landscape diversity. From the perspective of biospheric efficiency, Polar ice caps, vast tundras, and Arctic deserts are an enormous waste of space. These are dead zones where water, the foundation of all biochemistry, is locked in a solid, useless state as ice. These are regions where life pauses for half a year, where metabolism drops to zero, where cells must produce antifreeze just to avoid being torn apart by ice crystals. On Earth, millions of square kilometers exist in a state of permanent or seasonal coma. Winter on Earth is not just a season. It is an annual global catastrophe that life must endure by hiding, hibernating, or shedding its leaves. On our ideal planet, warmer by 5 degrees, this curse is lifted forever. Forget Arctic deserts. Forget the blinding white, lifeless ice caps that reflect sunlight back into space. In this world, there is no place for ice. Ice is an unknown physical anomaly here, something local inhabitants might only learn about through theoretical physics. This entire planet, from the equator to the poles, is one vast, continuous, endless tropical greenhouse. Thanks to the denser atmosphere we described earlier, and to the incredibly branched system of shallow oceans, heat from the orange dwarf is distributed across the planet with absolute mathematical uniformity. Water is the best accumulator and transporter of thermal energy in the universe. Millions of warm currents constantly circulate between endless archipelagos, smoothing out any temperature gradients. While on Earth, the temperature difference between the equator and the poles can reach 60 or 70 degrees, generating destructive hurricanes and violent winds. On a superhabitable planet, this difference is minimal. Even at the poles, where starlight falls at a low angle, the climate remains eternally warm, humid, and gentle. Like a subtropical summer evening, temperature is the key to the speed of chemical reactions. It is a fundamental law of thermodynamics. When the entire planet is evenly warmed, the biological engine never slows down. There are no seasonal pauses, no hibernation, no downtime. Vegetation grows, blooms, and bears fruit simultaneously and continuously throughout the entire year. Life surges in every cubic millimeter of water and air, 24 hours a day for millions upon millions of years. And within this global greenhouse exists a completely different atmosphere. It is warmer and therefore capable of holding far more moisture. Humidity is always near its absolute maximum. This is not the dry, biting air of Earth's winters that pulls moisture from your lungs. This is air you can almost drink. A dense, rich, warm mist that wraps around the crowns of giant forests in the morning and falls as soft, nourishing rain during the day. Water is not a scarce resource here. It is literally dissolved into the space around you. But the main difference in this atmosphere is not just water. The key difference is the gas that acts as pure rocket fuel for complex biology, oxygen. Thanks to the endless shallow seas, perfectly warmed and illuminated, and the boundless forests that never know winter, oxygen production on this planet operates with astonishing, overwhelming efficiency. The percentage of oxygen in this dense atmosphere is far higher than the meager 21% we have on Earth today. It could reach 30, even 35%. Oxygen is the energy currency of metabolism. The more of it there is, the more energy each individual cell in a multicellular organism can produce. Higher oxygen levels remove physiological limits on size, speed, and complexity. To even begin to imagine what a biosphere running on such an enriched oxygen mixture looks like, sounds like, and feels like, we must step back. Not to modern jungles like the Amazon or Congo, which are far too weak for comparison, but deep into Earth's own past, more than 300 million years ago, into the extraordinary era known as the Carboniferous period. Back then, due to a unique combination of geological and biological factors, oxygen levels on Earth rose to an unprecedented 35%. The consequences were staggering. It was an age of giants. Imagine that ancient landscape, now preserved only as black coal deep underground. The forests of the Carboniferous were nothing like ours. Not oaks, not pines, not birches, but vast, dense, impenetrable thickets of giant club mosses, ferns, and horsetails. Plants that today barely reach your knee once grew dozens of meters tall, forming a thick, multi-layered canopy that barely let sunlight through. Trunks several meters thick rose like columns in an endless green cathedral. But the most astonishing part of that world was its animal life. Insects and arthropods, which breathe through microscopic tubes rather than lungs, are limited in size today by low oxygen levels. But in the Carboniferous, that limitation vanished. Dense, oxygen-rich air allowed oxygen to penetrate deep into tissues, supporting massive bodies. The skies were patrolled by creatures like living nightmares, yet perfect in their design. Imagine Meganura, an ancestor of modern dragonflies, but with a wingspan of up to 70 centimeters. A dragonfly the size of an eagle. Its approach was not a gentle buzz, but a low, heavy hum, like a small helicopter cutting through dense, humid air. Below, in the rotting undergrowth, moved creatures of even more incredible scale. Arthropleura, a giant millipede over 2.5 meters long, a segmented, armored tank gliding silently across the forest floor. Giant scorpions roamed, some the size of dogs, alongside early amphibians resembling massive, sluggish crocodiles. This Carboniferous Earth is the closest sketch, the most accurate visualization of what the biosphere of a superhabitable planet might look like. A surplus of life. Gigantism, a relentless biological factory operating at maximum capacity thanks to heat, dense air, and oxygen abundance. But here lies the deepest and most tragic difference between our imperfect world and a true cosmic paradise. On Earth, the Carboniferous was only a brief, unstable episode, a temporary glitch in the climate system. It ended in catastrophe. Vast forests failed to decompose, locking carbon away. Oxygen rose to dangerously high levels, turning the atmosphere into a powder keg. Lightning triggered global wildfires that devastated continents. Eventually, falling carbon dioxide levels broke the planetary thermostat, plunging Earth into a deadly ice age. The giants vanished. Earth simply could not sustain such biological intensity. But on superhabitable planets orbiting stable orange dwarfs in perfect thermal and gravitational balance, this state is not temporary. It is the norm, not millions but billions, tens of billions of years. Imagine evolution uninterrupted by ice ages, global fires, or asteroid impacts, deflected by a thick atmosphere and powerful magnetic field. On such a world, the Carboniferous never ended. It only evolved. Gigantism would give way to unimaginable refinement. Over billions of years, giant insects could evolve nervous systems more complex than those of birds. Forests would become interconnected superorganisms, their root systems communicating and distributing resources like a planetary neural network. Here, life is no longer a passenger clinging to geology. On Earth, life adapts to volcanoes, earthquakes, and shifting continents. But on a superplanet, a turning point is reached. Life accumulates such immense mass and energy that it becomes the dominant geological force. It no longer adapts to the planet, it shapes it. Coral reefs spanning millions of square kilometers build continents from calcium. Root systems grind rock into fertile soil faster than erosion ever could. The biosphere precisely regulates atmospheric composition, maintaining perfect balance without overheating or cooling. It holds the planet in a stable, warm equilibrium. This is a world where energy is not scarce. It overflows through every cell, every drop of dew, every warm gust of wind carrying vast, colorful seeds over endless forests beneath a soft orange sun. And most importantly, this biosphere has achieved something profound: the absence of fear. Life on Earth is fundamentally traumatized, shaped by winter, hunger, extinction. Our evolutionary code is built on fear. But in a superhabitable world, life has never known global cold. No species remembers ice. No mass extinction from climate collapse exists in its genetic memory. There is no need to hide, no need to compete for survival. All energy is directed toward growth, flourishing, and endless complexity. This is a world of absolute evolutionary luxury, where life does not struggle to survive but celebrates its eternal dominance over matter. We have come a long way. We have proven that Earth is not ideal. We have shown that our sun is not the best star. We have realized that our mass, our gravity, our atmosphere, all of these are compromises, not the pinnacle of what is possible. In our imagination, we constructed an ideal world, warm, humid, rich in oxygen, and bathed in generous orange light. But it is easy to dismiss all of this as poetic fantasy, as an intellectual exercise, beautiful but unfounded. After all, what is a theoretical world built from mathematical formulas and computer models? It is a mirage, a sandcastle that has never existed in physical reality. One might say yes, perhaps such conditions are theoretically more favorable. But does that mean such planets actually exist somewhere in the universe? Perhaps the perfect alignment of all parameters is so rare that it never occurs in practice. Perhaps Earth is unique after all, and we are simply too harsh in judging it. This is where science delivers a decisive blow to the last bastion of our optimism. In 2020, a paper published in the journal Astrobiology forever changed the way astrobiologists think. Its authors, René Heller of the Max Planck Institute for Solar System Research in Göttingen and Dirk Schulze-Makuch of the Technical University of Berlin, did something simple, yet astonishingly bold. They did not merely theorize. They took a large body of real astronomical data collected by the Kepler telescope, one of NASA's most successful missions in the search for exoplanets, and applied to it a set of superhabitability criteria. Their approach was rigorous and methodical. They evaluated each planet through 7 fundamental filters. The first, the age of the star system. It must be older than our solar system, giving evolution more time to operate. The second, the type of star. It should be an orange dwarf of spectral class K with a longer and calmer lifespan. The third, stellar stability, minimal flares, and ultraviolet radiation. The fourth, planetary mass, between 1 and 2 Earth masses, enough to retain a dense atmosphere and sustain geological activity without excessive pressure. The fifth, average surface temperature between 5 and 18 degrees Celsius compared to our current 14, slightly warmer. The sixth, the presence of liquid water and extensive shallow continental shelves. The seventh, the presence of a natural satellite to stabilize axial tilt. They methodically sifted through the entire catalog. Thousands of planets, thousands of deviations, mismatches, failed candidates. And they found 24. 24 real, documented, astronomically confirmed objects that meet the criteria of superhabitable worlds better than Earth. This is no longer theory. This is not an imagined paradise. These are coordinates, real points in real space, tied to real stars that telescopes have observed for years. They exist. They are out there. And now we know their names. Let us walk through this list slowly. Let each name resonate as it deserves. Kepler 442b, perhaps the most famous and best studied of the 24. It orbits an orange K-class dwarf in the constellation Lyra, approximately 1,200 light-years away. Its mass is about 1.3 Earth masses, large enough to retain a denser atmosphere and sustain an active geological cycle. It receives about 84% of the stellar radiation that we receive, while residing in a more stable habitable zone. But most importantly, its star. It burns more slowly. It may allow this planet to maintain a stable environment not for 4 billion years like Earth, but likely 8, 10, or even more billion. That means evolution on Kepler 442b has had, or will have, twice as much time for its endless experiments. Imagine what might happen to intelligence given twice the time it took us to go from single-celled organisms to building radio telescopes. Kepler 69c. Another member of this elite group. A planet in the constellation Cygnus, orbiting within a region where liquid water can exist. Its star, though similar to our Sun, is slightly smaller and dimmer, giving the planet a longer lifespan. Kepler 69c is larger than Earth, about 1.7 Earth radii, which may mean a denser atmosphere, deeper oceans, and stronger plate tectonics, continuously mixing minerals and supporting the chemical diversity necessary for complex life. Kepler 1126b. Less known to the public, but no less impressive. Its star system is almost 2 billion years older than ours. 2 billion extra years of evolution. 2 billion years during which civilizations could have risen and fallen. 2 billion years in which some form of consciousness might have looked at its own sky and built its own mathematics, its own physics, its own understanding of the universe. KOI 5715.01. Potentially one of the most intriguing candidates. Located about 6,000 light-years away, orbiting a stable K-class star. Its estimated mass falls within the golden window of 1 to 2 Earth masses. Its estimated surface temperature is slightly higher than Earth's, which, given sufficient water, could mean a far more active biosphere. Yet it remains a candidate. Confirmation requires further observation. Scientific caution does not diminish the possibility of what may exist there. TOI 700. Although not part of the original list due to its later discovery, it is often discussed in the same context. Discovered by the TESS mission in 2020, it is an Earth-sized planet in the habitable zone of a red dwarf. While red dwarfs are generally less ideal due to frequent flares, TOI 700d shows that even less perfect stars can host potentially habitable worlds, and 19 more names. 24 points in the sky looking back at us as we observe them through telescopes. But all this talk of planets and coordinates can feel abstract. Let us pause and truly grasp what these 24 objects mean. The Kepler telescope, during its mission from 2009 to 2018, observed only a tiny fraction of our galaxy, about 0.1% of the sky. Imagine standing in an infinite forest at night, trying to describe all the trees by looking through a keyhole. That is what Kepler did. Through that keyhole, it found 24 planets better than Earth. Now consider the math. If 0.1% contains 24 such planets, then across the entire galaxy, with 200 to 400 billion stars, there may be tens or even hundreds of billions of superhabitable worlds. Not thousands, not millions, billions. The universe is filled with places better than our home. This is not exaggeration. This is statistics. And yet, they are unreachable. Kepler 442b lies about 1,200 light-years away. A spacecraft like New Horizons traveling at about 50,000 kilometers per hour would take approximately 26 million years to get there. 26 million. Even at 1/10 the speed of light, the journey would take 12,000 years. We know the address of paradise, but between us and paradise lies an abyss of time. And so we arrive at a deeper question. If these worlds are better, if they are older, if life had more time, where is everyone? Why do we hear nothing? Why has no one come? Why do we shout into the darkness and receive no answer? We stand on the edge of that answer. And it may be far more unsettling than anything we have discovered so far. We have just held in our hands a list of 24 planets. We know they exist. We know that some of them are billions of years older than Earth. We know that by every parameter, conditions there are more favorable for the evolution of complex, multicellular, intelligent life. And now it is time to ask the question that follows from this knowledge as inevitably as night follows day. A question that scientific papers hide behind careful, restrained wording, but which every researcher feels at the very core of their work. If these planets are so wonderful, where is everyone? This question is known in science as the Fermi paradox. It takes its name from the famous physicist Enrico Fermi, who in 1950 at a lunch table in Los Alamos, in the middle of an ordinary conversation about flying saucers, suddenly asked his colleagues, "Where is everybody?" The question was asked lightly, almost jokingly, but it landed like a heavy stone and echoed long after the plates were cleared. Here's the essence of the paradox. The universe is vast and very old. Our galaxy alone, the Milky Way, contains between 200 and 400 billion stars. Most of them have planets. Many of those planets lie within habitable zones. Some of those planets, as we now know, may even be better than Earth. The galaxy is about 13 billion years old. If even a fraction of star systems developed intelligent life that began advancing technologically even 1 billion years before us, where is the evidence of their existence? Why do we not see their ships? Why do we not hear their signals? Why is the sky so completely, overwhelmingly silent? There are dozens of proposed explanations for this silence. Each of them is unsettling in its own way. Perhaps intelligent life is extremely rare, and we are truly alone. Perhaps advanced civilizations inevitably destroy themselves upon reaching a certain level of technology. Nuclear weapons, artificial intelligence, ecological collapse. Perhaps the galaxy is already inhabited, but we are too primitive to notice signs of alien presence, just as ants do not notice Wi-Fi. Perhaps interstellar travel is physically impossible even for the most advanced civilizations due to the same speed of light limitations that imprison us. But the concept of superhabitable worlds offers an explanation that does not fit into any of these categories. It is not terrifying. It is not apocalyptic. It is simply insulting. Perhaps they are silent because they are not interested in coming here. Think about it. If you live in a warm, spacious house overlooking the sea, with a perfect climate, abundant gardens, and limitless resources, would you travel to visit a cold, windswept industrial district at the edge of a city? Would you feel an irresistible urge to spend years of your life and enormous resources to reach a place that is either too cold or too hot, where the ground shakes and the sky occasionally burns with falling asteroids? One might object a sufficiently advanced civilization driven by curiosity would explore everything regardless of comfort. But that objection is based on our own standards. We explore because we are pushed by scarcity, danger, and competition. We are driven forward by cold, hunger, and fear. We build ships because we have always had too few resources and too many threats. Our curiosity is a direct derivative of our survival. But what if a civilization that evolved on a superhabitable planet never experienced those pressures? What if their fundamental psychology, their core motivations, shaped by billions of years of evolution in conditions of abundance rather than scarcity, are fundamentally different? What if they simply do not feel that sharp, painful call of the unknown that drove our ancestors across oceans and deserts? We have always imagined contact with extraterrestrial intelligence as a meeting of equals or as a dramatic invasion. Science fiction shows us diplomatic negotiations in orbit, or terrifying invasions, or hostile armadas darkening the sky. But we almost never consider the scenario in which another civilization is simply uninterested, not hostile, not friendly, just indifferent. The way we are indifferent to the largest anthill in the forest near our city, We know it is there. We even study it sometimes. But we do not try to establish radio contact with it. And here, the concept of superhabitable planets delivers a psychological blow that is difficult to recover from, because if this explanation is even partially correct, it means that our place in the universe is not merely modest, it is peripheral. We do not live in just one of many places. We live in a depressed neighborhood of the galaxy, a place where natural conditions are so mediocre that more advanced neighbors do not even consider it worth visiting. We have sent radio signals into space. The Arecibo message of 1974, a mathematically encoded portrait of our civilization sent toward the globular cluster M13, the Voyager Golden Records, with music, maps, and greetings in 50 languages attached to probes now drifting through interstellar space. Cosmic call and teen-age message. Targeted radio transmissions to nearby stars. What if these signals and probes are a deep, sincere cry to the universe? We are here. We exist. Notice us. And what if the response, if it ever comes, is not a greeting between equals, but the polite indifference of an expert briefly examining an interesting but insignificant artifact before returning to more important matters? But there is another level to this psychological blow, a deeper one, not just about our place in the galactic hierarchy, but about our place in nature itself. If humanity somehow, even in imagination, stood on the surface of Kepler 442b, what would we be there? Let us begin with the most obvious, gravity. This planet is about 1.3 times more massive than Earth. That means gravity is roughly 30% stronger. A person weighing 70 kilograms on Earth would feel like 91 kilograms there. Not too bad, it seems. But do not rush. The spine, the heart, the blood vessels evolved under Earth's gravity. Within hours, increased compression of spinal discs begins, and the heart must work harder to pump blood upward. Long-term exposure leads to progressive changes in the skeleton, cardiovascular system, and muscles. Local organisms, by contrast, would be perfectly adapted. Stronger bones, more powerful muscles, more compact bodies. Next, the atmosphere, denser than Earth's, potentially with higher oxygen content to sustain a rich biosphere. For native life, it is home. For us, potential hyperoxia. Excess oxygen is toxic to the human body. Above 30% concentration, oxidative stress, lung damage, and seizures begin. On a planet where evolution has optimized every cell for a richer atmosphere, we would suffocate from the very element we breathe. Then, biology. If the planet is truly superhabitable, its biosphere would be dense beyond imagination. Every surface alive with organisms we have never encountered. Microbes, fungi, plants, animals, all evolved in isolation for billions of years. Our immune system would recognize none of them. No antibodies, no memory, no prepared response. We would stand defenseless before billions of unknown microorganisms. Even harmless ones could trigger catastrophic immune reactions. We would arrive in paradise and immediately fall ill. We would stand beneath an orange sun, gasping for breath, bent under our own weight, coughing from alien spores, while around us native beings moved with ease, strong, adapted, at home in every inch of that beautiful, deadly world. And here, in this image of ourselves as weak, sick outsiders in a sickaspader kush per atmois, lies the deepest psychological to heart of this story. We are used to thinking of humans as the pinnacle of nature, Homo sapiens, wise man. We named ourselves wise. We build cities, compose symphonies, fly into space. We are the only species that knows it exists. And throughout our history, we have taken this as a sign of superiority. We are the crown of creation. But what if we are simply children of a very difficult childhood? What if our intelligence is not a mark of superiority, but a scar, a result of the fact that our world never let us rest? We are intelligent because we were constantly threatened. Our brains evolved to solve survival problems in a harsh, unstable, dangerous environment. Fire, weapons, agriculture, every step of our development is a response to hardship. And so a terrifying question emerges. If our ancestors had been born on a superhabitable world, warm, abundant, stable, would we have become intelligent at all? Evolution does not strive for intelligence. It strives for survival. The brain is an extremely expensive organ. It consumes 20% of our energy while making up only 2% of body mass. Nature does not build expensive organs without need. In stable abundance, simplicity is more efficient. Some scientists seriously suggest that in ideal conditions, evolution might stop at a form of highly successful, long-lived but non-intelligent life. Large, slow, content creatures grazing in warm, shallow seas for billions of years, never needing to think abstractly, never needing to count the stars. In paradise, there is no reason to build rockets. This idea overturns our entire system of values. We thought intelligence was a reward. But what if it is a trauma response? We think because we had to. And if that is true, then on those perfect worlds beneath orange suns, there may be no one looking at the stars. Only vast, unconscious, perfect life. No telescopes, no Fermi paradox. Only abundance and silence. Or, and this is even more unsettling, perhaps there is intelligence, but it is so different from ours that we have come a long way. We began with a pale blue dot in an old Voyager photograph and arrived at the threshold of questions that have no simple answers. We took Earth apart like a mechanism, examined its faults and fractures, compared it to what it could have been. We found 24 planets better than our home. We asked where everyone is and received answers, each worse than ignorance. And now, it is time to stop. Not for the sake of an optimistic conclusion. Our journey has been too honest for cheap comfort, but to look at everything we have learned and ask, what do we do with it? How do we live with this knowledge? And does it really change anything? Let us begin with the most obvious destruction this journey has inflicted on our self-image. Earth is not the crown of creation. This is a fact, not a poetic metaphor, not a philosophical provocation, but a conclusion supported by astronomical observations, astrobiological models, and the real coordinates of 24 objects. Our blue sphere is one of billions of planets and far from the best. Our sun is neither the most stable nor the longest-lived star. Our mass, our gravity, our temperature regime, they are a compromise, not an optimum. This shatters 2,000 years of anthropocentric philosophy with a single mathematical equation. Humanity has already endured two great demolitions of its central role. The first, Copernicus, who expelled us from the center of the solar system. The second, Darwin, who stripped us of a special supernatural origin. We're just another species on one of the planets orbiting one of the stars. Each time we adapted. Each time we found a new form of dignity. Perhaps we are not at the center, but we are the most intelligent. Perhaps we are animals, but animals capable of understanding the universe. But now the concept of superhabitable worlds delivers a third blow. We may be intelligent, but perhaps only because our home forced us to become so. We may explore the universe, but within it exist places where evolution had twice as much time and 10 times more favorable conditions. And what has grown there over those extra billions of years, we cannot even imagine. There is a temptation to fall into despair, to feel this smallness, this peripherality, this second-rate nature of our home, and decide that none of it matters, that we're a random mistake of nature in a forgotten corner of the galaxy, and our civilization, our science, our art, just the bustle of ants on the shoulder of a cosmic highway. But this is where things become most interesting. Because if you think more deeply, if you truly stop and reflect on the paradox of our existence, you discover something strange and unexpected. Our imperfection is our greatest defining achievement. Think about it, there, on those perfect superplanets beneath orange suns, if there is no intelligence, or if there is a kind of intelligence that has merged with nature and feels no need to move further there, is no one asking questions. No one is looking at the sky and thinking, what is there? What lies beyond? Why is everything the way it is? A question is a product of dissatisfaction. It arises when reality does not match the desired, when something hurts, when something is missing, when there is a gap between what is and what could be. A well-fed, warm, protected organism in a perfect environment. It does not ask. It simply exists. We ask. We have always asked. We asked when we painted bison on cave walls in the dim light of fat lamps. And the question was, how do we preserve this moment? We asked when the first astronomers of Babylon counted the stars. And the question was, why did they move this way? We asked when Copernicus drew his diagrams, and the question was, what if we are not at the center? We asked today, when the James Webb Telescope looked into the earliest galaxies, and the question was, how did it all begin? Our mind is the child of suffering, but what it has created has gone far beyond survival. We began with fire to avoid freezing and arrived at quantum mechanics. We began by counting prey and arrived at the theory of relativity. We began with fear of storms and arrived at an understanding of electromagnetism. Every step from pain to knowledge, from lack of insight. And there is something almost sacred in this, not in a religious sense, but in the sense of the absolute paradox at the foundation of our existence. We are the most conscious product of the least perfect environment. We are the most curious species, born of a planet that tried to kill us 5 times. There is an idea expressed by physicist Freeman Dyson in a different context, but it fits perfectly here. The universe, in some sense, knew we were coming. He spoke of the fine-tuning of physical constants, but we can read this differently. The universe is arranged such that there are places of astonishing beauty and perfection, and places where scarcity and danger press on matter so intensely that matter learns to think. Both types of places are necessary. Perfect planets provide endless diversity and duration. Imperfect ones give rise to consciousness. We are a rare, perhaps unique, perhaps one of very few points in the universe where matter has learned to look at itself and ask why. And this is no lesser dignity than being inhabitants of a perfect paradise. It is a different dignity, not the dignity of comfort, but the dignity of understanding. Close your eyes. Imagine that other world. You already know its coordinates, 1,200 light-years to the left, slightly below the constellation Lyra, where an orange star has been burning slowly and calmly for 9 billion years. There a planet, slightly heavier than Earth, slightly warmer, with oceans stretching for thousands of kilometers in every direction, where water is never frozen even at the farthest poles. There are no glacial scars, no deserts dried by climatic cataclysms, no traces of mass extinctions in the rock layers. The land there is not an archive of disasters, but a continuous, endless poem of abundance. Forests grow where on Earth there would be barren plains. Coral reefs cover areas larger than our continents. The air is thick and warm, every breath filled with pollen and spores of thousands of species unknown to any of our languages. There, beneath an orange sun, right now, at this very moment, while you are reading this, something extraordinary may be happening. Some organisms may be dancing in the rhythm of chemical signals, unknown and beautiful. Some forest may be growing, its roots descending kilometers into the soil and intertwining with neighboring forests into a single planetary neural network of chlorophyll and minerals. Some pair of eyes, or something that serves as eyes, may be looking at the orange sun and not asking what lies beyond it, but simply feeling, simply existing, simply breathing. We will never reach it. Physics closed that door millions of years ago when it set the maximum speed of the universe and gave us no way around it. We look at that orange sunset through 1,200 years of cosmic distance, through the thin glass lens of a telescope, and see only a point of light in infinite darkness. But here's the strange thing. We see it. We small, fragile, vulnerable, born on an imperfect planet, under an unstable sun, in a dangerous corner of an average galaxy we have learned to see across 1,200 years of darkness. We have built machines capable of catching single photons that have traveled through emptiness longer than all of our recorded history. We have learned to read from those photons the mass of a planet, the temperature of its surface, and the composition of its atmosphere. We have learned to mathematically reconstruct conditions we will never experience firsthand. Nothing in the perfect biosphere of Kepler 442b, if there is consciousness there, could perform this specific act of knowing. Because this act is a product of pain. It is born of ice ages that forced our ancestors into cold caves to stare at fire. It is born of mass extinctions that cleared ecological niches and gave our evolutionary line room to grow. It is born of asteroids, volcanoes, and every other catastrophe with which our substandard home has generously supplied its inhabitants over 4.5 billion years. We are not a mistake of nature. We are its most unexpected, most paradoxical, and perhaps most unique result. In perfect conditions, nature creates life that is flawless, eternal, abundant but silent. In conditions of stress, danger, and scarcity, nature sometimes rarely, perhaps very rarely, creates something that begins to ask. And a question is not a weakness. A question is a special form of existence, perhaps the rarest in the universe. Our home is imperfect. It is cold and unpredictable. It has already tried to destroy us 5 times, and undoubtedly will try again. Our sun will one day expand and consume us. Our climate is unstable. Our resources are limited. Our gravity is too weak to hold the atmosphere forever against the solar wind. But this imperfect home is the only one we have, and it has made us into something that may not exist on all those perfect superplanets combined. It has made us beings who look at the sky and think. A Chinese astronomer looks at Kepler 442b through a telescope and thinks. An American schoolgirl reads about 24 candidates and asks why. A researcher at NASA builds a model of a perfect climate and feels a quiet longing for a place they have never been. These moments are no less significant than billions of years of calm abundance in warm seas beneath an orange sun. They are different. They are shorter, but they contain something those billions of years may lack: awareness. Awareness is the price the universe charges for an imperfect environment. It takes comfort, safety, ideal gravity, and an eternal orange noon. And in return, it gives you the ability to know that all of this exists. Close your eyes one last time. Imagine yourself standing on a night shore, our own, earthly, slightly cold, slightly damp, imperfect shore. Above you, the sky your ancestors once thought was a dome beneath which gods moved the stars. Now you know what truly lies beyond it. You know about billions of galaxies. You know about orange stars and superplanets. You know the coordinates of places where, perhaps billions of years ago, something began before which our civilization is only the first timid line of a long novel. You are a shadow at the edge of the galaxy. That is true. But you are a shadow that knows it is a shadow. A shadow that has measured the distance to the light and given it a name. And in a universe where most matter has never opened its eyes, that is not so little.